By the late 19th century, the wave nature of light was considered settled science. In 1887, Heinrich Hertz's experiments with electromagnetic waves appeared to confirm Maxwell's equations perfectly, establishing light as a continuous propagating wave. The core of this classical picture was the idea of continuous distribution. In this view, light energy is spread smoothly across an entire expanded wavefront, much like a swell of water moving through the ocean. Yet in that same year, Heinrich Hertz noticed a strange anomaly during his spark discharge experiments. He found that shining ultraviolet light onto a metal plate facilitated the escape of charged particles. These particles were electrons. Under normal conditions, they are held inside the metal by the attractive forces of positive ions. To escape the surface, an electron must gain a specific minimum amount of energy, a threshold known as the work function. Physicists assumed the continuous wave theory would easily explain how electrons absorbed this energy. But when they ran the numbers, the mathematical predictions of wave mechanics were completely inverted by experimental reality. This microscopic mismatch on a piece of metal exposed a fundamental contradiction that classical physics could not resolve. To measure this failure, researchers used an evacuated glass tube containing two metal plates. When light strikes the photosensitive emitter, it knocks electrons loose, which then travel across the vacuum to a collector plate. This flow creates a photocurrent. By applying a negative voltage to the collector, scientists could repel these electrons. The exact negative potential required to stop even the most energetic electron from reaching the plate is called the stopping potential, a direct measure of the electron's maximum kinetic energy. By isolating just two variables, the intensity of the light and its frequency, investigators discovered three paradoxes that the wave model could not explain. Classical theory predicted that a more intense light beam carries a larger wave amplitude. This larger wave should impart more energy to the electrons, causing them to be ejected with greater speed and higher kinetic energy. The data showed increasing light intensity increases the number of emitted electrons, but their energy remains unchanged. We see this in the voltage curves for different intensities. Brighter lights produce a higher saturation current, yet all curves converge at the identical stopping potential. The maximum kinetic energy of the emitted electrons is independent of light's intensity, directly contradicting classical wave mechanics. The second contradiction involved the color or frequency of the light. Wave theory suggested that any frequency should eventually eject an electron, provided the light was intense enough to deliver the necessary energy over time. In reality, if the light is below a specific threshold frequency, no electrons are emitted at all. Below this cutoff, even the most intense light beam results in zero emission. Once crossed, light frequency determines electron energy. Higher frequencies result in a more negative stopping potential. Plotting this shows a universal linear relationship across metals. Each material has its own unique threshold frequency, a minimum requirement classical waves couldn't explain. Classical physics offered no explanation for why the color of the light dictates the energy of the electron, while the total amount of light energy has no effect. The most significant conflict, however, concerned the timing of the emission. According to the wave picture, light energy is spread across millions of atoms on the metal surface. If the energy is distributed this thinly, it should take a single electron hours to absorb enough energy from the continuous wavefront to overcome the work function and break free. Instead, the emission is instantaneous. Even when the light is exceedingly dim, electrons are ejected in a billionth of a second or less. This immediate reaction proves that light energy cannot be delivered as a slow-filling, continuous wave. Resolving these paradoxes required a complete departure from 19th century electromagnetism. In 1905, Albert Einstein proposed that light does not behave like a continuous wave during its interaction with matter. He suggested that radiation is made of discrete, indivisible packets of energy called quanta, or photons. The energy of each individual photon is determined solely by its frequency. This turns the photoelectric effect into a one-to-one interaction. If a single photon has a high enough frequency, it transfers all its energy to a single electron instantly. This explains why emission is immediate and why a minimum threshold frequency is required. In this model, intensity simply refers to the number of photons hitting the metal per second. More photons eject more electrons, but they don't change the energy of each individual impact. Robert Millikan's precision experiments eventually confirmed this equation, and Einstein was awarded the 1921 Nobel Prize in Physics for his discovery of the law of the photoelectric effect. By proving light behaves as a particle when interacting with matter, the photoelectric effect established the dual nature of radiation, providing the experimental evidence that made quantum mechanics necessary.